This video is an introduction to trigonometric functions using the unit circle as a way to understand and obtain them. Let's begin with the unit circle. What is it? It's a circle of radius 1. This means its circumference is 2 pi. It is also centered at the origin of a rectangular coordinate system. Now let's say we want to travel t units along the circumference of the unit circle, beginning at 1, 0. The figure on the left shows a ray in red of length t beginning at 1, 0 and pointing straight up from there. And the figure on the right shows the same ray beginning at the same point, pointing straight downward. This shows how long t actually is. Both figures also show arcs of length t beginning at 1, 0 and coinciding with the circumference of the unit circle. In each case, the arc terminates at point P located at x, y. We say that point P corresponds to t. We relate P, which is expressed using coordinates x, y, to t by using trigonometric functions. For example, we relate the y-coordinate of P to t by saying that the sine of t is equal to y. Similarly, we relate the x-coordinate of P to t by saying that the cosine of t is equal to x. And as long as x does not equal 0, we can say that the tangent of t is equal to the ratio of y to x. We define 3 additional trigonometric functions, cosecant, secant, and cotangent, as the reciprocals of sine, cosine, and tangent of t, respectively. If we have a certain point P, say, as in this case, minus 1/2, comma, the square root of 3/2, that's on the unit circle, it is straightforward to find the trigonometric functions. For instance, the sine of t is going to be equal to y, which is equal to the square root of 3/2. And the cosine of t is equal to x, which here is going to equal minus 1/2. And the tangent of t is the ratio of y to x, and that, in this case, is going to be negative the square root of 3. The cosecant, secant, and cotangent of t are the reciprocals of these functions, respectively. Now let's consider an equation that we saw in the last video, that is, s is equal to r times theta, where s is the angle subtended by the central angle theta, and r is the radius of a given circle. For the unit circle, r is equal to 1, and here t is equal to s, so we have t is equal to theta. This means that t and theta are equivalent, and that we can say that any given trig function that is a function of t is equal to the same trig function of theta. The angle theta may be expressed in degrees or radians, and we will use both interchangeably. Now let's consider the trig functions of quadrantal angles. A quadrantal angle is one that is in the standard position and has a measure that is a multiple of 90 degrees or pi/2 radians, such as 90 degrees, 180 degrees, 270 degrees, and so forth. A quadrantal angle will have its terminal side lying along either the x or y axis. Some examples of quadrantal angles are shown in the figures here. Because of the way they're defined, we know that the xy coordinates of a point on the unit circle correspond to cosine theta, sine theta, and we can use this fact to help us find the trig functions for quadrantal angles. These functions and their values are summarized in Table 2 on page 370 of the textbook. The values are valid for any quadrantal angle, including negative ones or ones greater than 360 degrees or 2 pi. Now let's look at the trig functions of pi over 4 radians, or 45 degrees. This angle bisects the 90-degree angle of the unit circle quarter in the first quadrant. So P is lying halfway along the arc of the circle circumference between 1, 0 and 0, 1. In fact, P lies at the intersection point of the circle x squared plus y squared equals 1, and the bisector of the 90-degree angle, y is equal to x. We can use this fact to solve for x. Let's start with the equation of the unit circle. Since y equals x, we can substitute x for y. We sum the x squared terms on the left, and solving for x, we get either 1 over the square root of 2 or minus 1 over the square root of 2 as the values. Since the point x, y lies in the first quadrant, we know that x cannot equal minus 1 over the square root of 2. So x equals 1 over the square root of 2, and so does y, since they must be equal. So for theta equals pi over 4, which equals 45 degrees, the sine of theta is equal to y, which is 1 over the square root of 2. The cosine of theta is equal to x, which also equals 1 over the square root of 2. And the tangent of theta, y over x, equals 1. And cosecant, secant, and cotangent of theta are reciprocals of sine, cosine, and tangent of theta, respectively. Now let's consider the trig functions of pi over 6, which is 30 degrees, and pi over 3, which is 60 degrees. We do this by analyzing a right triangle containing the angles 30 degrees and 60 degrees, and this is called a 30, 60, 90 triangle. This triangle has a hypotenuse of 1, and we would like to know the lengths of the other sides. When we add an identical triangle back to back with the original, we obtain a new triangle that is equiangular, which means it is also equilateral. We already know that side C is equal to 1, so the side that is 2a long must also equal 1. This means a must equal 1/2. Now we use the Pythagorean theorem to find b, the only side in the original triangle we still don't know. We substitute in the values of a and c and solve for b. And we find that b is equal to the square root of 3 over 2. Let's use this information to find the trig functions of the angle pi over 3, which is also 60 degrees. In the figure, a 30, 60, 90 triangle is drawn within the unit circle, with pi over 3 as the central angle. From this we can see that sine pi over 3 is equal to the square root of 3 over 2, and that cosine of pi over 3 is equal to 1/2, and that tangent of pi over 3 is equal to the square root of 3. And as before, the inverse functions, the reciprocal functions are shown. A summary of these functions and of the trig functions of pi over 6 and pi over 4 can be found in Table 3 on page 374. We can use these results to help us find the trig functions of certain other angles. Let's start with theta equals pi over 4, which is 45 degrees. In the figure we see this angle and the point on the unit circle that corresponds to it, the square root of 2 over 2, comma, the square root of 2 over 2. By symmetry, we know the point on the unit circle that corresponds to 3 pi over 4. The one that corresponds to 5 pi over 4, and the one that corresponds to 7 pi over 4. And these respective points with their own xy coordinates can be used to obtain trig functions for all these angles. The same approach can be used for certain angles related to pi over 6, which is equal to 30 degrees. We begin with the point on the unit circle that corresponds to pi over 6, that is, the square root of 3 over 2, comma, a half. By symmetry, we can obtain the point on the unit circle that corresponds to 5 pi over 6, or 150 degrees. We can also find the one that corresponds to 7 pi over 6, and the one that corresponds to 11 pi over 6. And we can use the same approach for selected angles related to pi over 3, which is 60 degrees. We begin with the point 1/2, comma, square root of 3 over 2, the point on the unit circle that corresponds to theta is equal to pi over 3. By symmetry, we can obtain the point that corresponds to 2 pi over 3, or 120 degrees, and the one that corresponds to 4 pi over 3, and the one that corresponds to 5 pi over 3. Our use of symmetry allows us to obtain exact values of trig functions for a fair number of angles. The unit circle is very useful for obtaining trig functions of angles, but we can also obtain them for non-unit circles. Let's consider P equals x comma y, a point on a circle centered at the origin, that is, of radius r. Let's say there is a point P star, P asterisk, which equals x asterisk comma y asterisk, and it's on a unit circle that is concentric with the other circle of radius r. Both of them are shown in the figure. Both of these points correspond to the angle theta. If we draw a line perpendicular to the x-axis from point P to point A on the x-axis, we form a triangle, OAP. And if we draw a line perpendicular to the x-axis from point P star to A star, also a point on the x-axis. When we do that, we form a triangle O, A star, P star. These two triangles both contain the angle theta. Both have a right angle at point A, and so the angle whose vertex is at P must equal the angle whose vertex is at P star. So OAP, that triangle, and the triangle OA asterisk, P asterisk are similar triangles. This means that ratios of corresponding sides of these triangles are equal. And because that's true, we can say that sine theta is equal to y over r, cosine theta is equal to x over r, and tangent theta is equal to y over x. Note that when r equals 1, these values look like the ones we already obtained using the unit circle. As expected, the functions cosecant, secant, and cotangent here are reciprocals of sine, cosine, and tangent, respectively. Now we are ready to solve some problems. We have a circle with position angle theta with point on the circle, where the terminal side of the position angle terminates 4, minus 3. We'd like to find the trig functions. Even though we don't know theta, we can find its trig functions easily. First, we determine the radius of the circle. The xy values must satisfy the equation x squared plus y squared is equal to r squared. Using the coordinates given, we find that the radius is equal to 5. We find sine, cosine, and tangent of theta using the definitions, and the reciprocal functions as well. Now let's do a word problem. Say we have a sheet of metal that is 12 inches wide. We won't concern ourselves with its length. We want to bend it to make a rain gutter. The center of the gutter is 4 inches wide, and the sides are bent up at an angle of theta from the horizontal. We want to find the cross-sectional area, the amount of rain that the gutter can carry. That's marked with the blue dotted lines. The area of this rain gutter can be thought of as having three parts: a rectangle in the middle with area 4y, where y is the height of the greatest amount that the gutter can carry. It is the distance between the bottom of the central part of the gutter and the horizontal dotted blue line. The other two areas are triangular and both are the same size. We recall that the area of a triangle is 1/2 times the base times the height. Here, the base is x, the width of a triangle, and the height is y, the same height as the rectangular portion of the area. Sine theta is defined as y over r, and here r is known. It is 4, the length of the slope part of the gutter. Cosine theta is defined as x over r, and again, since r is equal to 4, this means x over 4. We can express y as 4 sine theta, and we can express x as 4 cosine theta. The total cross-sectional area of the rain gutter is the area of the rectangle plus 2 times the area of one of the triangles, since the triangular areas are identical. The area of the rectangle, 4y, can be written 4 times 4 sine theta, and the area of the two triangles can be written as 2 times the area of one of the triangles, and that would be 1/2 times the base, which is x, which is 4 cosine theta, times the height, which is y, which is 4 sine theta. This simplifies to the total area equaling 16 sine theta plus 16 sine theta times cosine theta. We can factor this, factoring out 16 sine theta, and we're left with 16 sine theta times 1 plus cosine theta. When theta equals 30 degrees, the total cross-sectional area is 14.93 square inches. When we increase the angle to 45 degrees, then the cross-sectional area also increases to 19.31 square inches. Finally, if we increase theta to 60 degrees, then the cross-sectional area also increases, this time to 20.78 square inches.